Not, let's thank our speaker again. Thank you.
Thank you very much.
Our next speaker is Nick Pedatella from UCAR. Talk about the impact of increasing the number of radio occultation observations.
Okay. Yeah, so I will present on impact of large numbers of RO data on ionosphere and thermosphere data assimilation model. So really the focus of this is to look at if you have a larger number than we currently have for a data assimilation model, how that would impact your specification of ionosphere and then also the thermosphere as well, since we have a coupled model. And a few studies have looked at this before, but they've been a bit limited in terms of the kind of number of data that they go out to. So I apologize, this figure is a bit blurry, I think, when I convert to the PDF, but I think you can see the main point. So this is basically a metric ranking versus observation count here, and it only goes out to about 7,000. And so lower number here is better, and you can see there's a general trend towards being better, but only out to 7,000 occultations per day. So what I did in this study is basically take the Romex data locations from UCAR and assume that that's the same location we have ionosphere data, and then run an Aussie with that data. So then we can look at the impact of up to, say, 30,000 or so electron density profiles per day in the data assimilation model. And the background model used here for all these experiments is the WACMX model, which is a whole atmosphere model going from surface up to about 500 kilometers with fully coupled ionosphere and thermosphere physics. And then the data assimilation is implemented using the DART ensemble common filter framework. And so these, just a bit of setup on the Aussie experiments that I run here. So the nature or truth run was run with a biased sort of forcing from the sun and then also geomagnetic activity. And then we run the data assimilation with a lower value and see how the extent to which we can recover this sort of bias. And this is a method used historically by other groups as well. And here on the right this is showing thermosphere density, so you can get a sense of the magnitude of the bias, latitude versus longitude at one snapshot. This is what we're kind of assimilating into, and this is the truth. So you can see the bias is quite large in this case in terms of thermosphere neutral density. And so I ran 4 data assimilation experiments here. And as I said, I just assume, wherever you had a neutral atmosphere profile from a Romex mission, we have an ionosphere profile there as well. And we assimilate, rather than slant tech, just the retrieve profile. And then in the observation error is added that's consistent with basically Abel retrieval errors, which is the dominant error. And I'll show on the next slide the 4 experiments that are run in this case. And then really these Aussies give us a sense of how the impact of going out to 30,000 profiles per day would impact the ionosphere and thermosphere. So these are the experiments that were run. So this is the number of occultations for the 3 experiments, and then the 4th experiment is a control with no RO observations. So experiment 1 is in black here. This is just using Cosmic 2 data. And so the black would be a global count for Cosmic 2, it's just low latitude. And the dashed here is just a low latitude count. And the reason I use that is some of the statistics later I'll show just for low latitude. So that's a relevant number as well. And then experiment 2 is in green here. And this is all the Romex data. One thing to note here, this number is a little bit lower because I originally took these from an earlier UCAR version that didn't have all of the Spire data. So that's why you see a slightly lower number. And then in the equatorial region, it ends up being around 20,000 per day. And then experiment 3 here is somewhat of a middle ground, which is Cosmic 2, Spire, and then Yunyao. And that gives you somewhere in the middle between the sort of Cosmic 2 only and then the all Romex experiment. And I think this just shows the spatial density. So for experiment 1, this is the daily number of occultations per 5 by 5 cell averaged over the time period. You see, obviously, it's focused in the equatorial region when we just have cosmic 1. Experiment 2 does give you, global coverage. And then when we just do the 3 satellite constellation, it's fairly good, both, in the equatorial region, but also some more coverage at high latitudes. The local time, as I think has been shown in a number of other presentations, is quite, non-uniform in these experiment 2 and 3. I don't investigate how that, impacts the results, but I think that's as important thing that we need to consider in the future, especially for the ionosphere, which has strong local time dependence. So here's the kind of global scale results if you just look at root mean square error and bias. So left is the root mean square error, right is a bias, and these are altitude versus the error. And here's the control in gray, black with just cosmic 2, and then purple for experiment 3, and then all Romex in the green. Obviously, going from cosmic to a global constellation gives you a significant reduction in error when you're doing a global statistic, since you have observations everywhere instead of just in the equatorial region. But adding these extra observations does reduce the error further, something about 8% around 300 kilometers. So there is value in going from these additional data. But that's looking at global. And an interesting thing is to look at just the low latitude region where cosmic is focused. And then you can really compare how the observation density impacts the sort of directly the errors. So again, this is root mean square error and a bias for the control, and then the cosmic 2 experiment, the sort of 3 constellation experiment, and then all of Romex. And this is just low latitude. So you're not seeing a impact of having, additional data outside of where cosmic 2 is. It's just adding more density within that low latitude region. And here you do see, still further reduction in the error at the low latitude region by going from something like 15,000 to about 20,000 at the low latitude region is what you have here. So there is, further impact in these experiments. And an interesting thing to look at is, since we have a physics-based model, does it impact the short-term forecast in the model? And so the dashed lines here are just the 1 hour forecast. And if you do see a slight reduction, there's not as much here for the experiment 2 versus experiment 3, but going from, say, cosmic to a much denser, about doubling the number of low latitude occultations does reduce the error quite a bit, even in the sort of short-term forecast that you get out of the model. Here is just looking at some of the summary statistics in a more numerical form than the graphs. This is all results at low latitudes again, looking at 300 kilometers. And really, I would just focus on the percentage errors here and look at the difference between experiment 2 and experiment 3. And you see that experiment 2 tends to be better in terms of the reduction by adding more data, but it's on the order of a few percent in these experiments, going from the sort of full Romex set just to the 3 satellite that we consider in that experiment. And here is looking at it in a sort of same statistics, but then plotting it against the number of occultations per day. Again, just a low latitude region where you can directly compare the numbers and not confound it with just having data at a different region. And you see it does decrease a lot from, say, 6,000 to somewhere around 13,000, and then maybe a little bit less of a decrease from 13 to almost 20. But it depends what you look. Some of, say, the bias statistics here, where lower would be better, higher on this graph, which is actually a lower number near 0, is better. Still seems like it's going up quite a lot. So it's probably not maybe even saturated at that value, but we haven't run a greater number of occultations. And then another interesting thing to look at is the thermosphere neutral density results. Since we have a coupled model, we can just leverage the correlations in the model and adjust the neutral thermosphere to get the thermosphere neutral density from the ionospheric occultations. This is looking at global root mean square error. This is a function of time for, say, a 4-day period here in the late September, and the control. And then just cosmic does give you actually quite a significant reduction in the thermosphere neutral density. And then you'd see even further reduction for these other two experiments. And again, the sort of full Romex set gives you maybe a 3% or so improvement relative to the case where we just did, the cosmic, Spire, and Yuan Yao. But you do get quite a lot just from cosmic alone. So you go from, this to say 22% improvement, and then another, say 10% from adding these additional data. And we did look, you can always run forecasts. You can debate how meaningful they are. We initialized some forecasts here on this day and just ran it, free running with no more data assimilation to see. I don't think there's a significant impact on, the thermosphere density forecast. At least, this was just one instance, so I wouldn't put too much into it. But in this case, it doesn't seem too much of a impact in terms of this sort of skill, but I don't think I would put a lot of faith in, one forecast initialization. And so just as a summary, I think these results show that for, thermosphere and ionosphere specification in very short term, say 1 hour forecasting, up to 30,000 occultations per day in these, at least in these Aussie experiments, doesn't seem to saturate the errors so far. One thing I think it's important to consider is, this setup is a bit limited in the way we set up the Aussie, and I didn't really consider observation local time coverage. So I think if you look at the errors, at different local times, I would guess they're quite dependent on, what the local time sampling of the distribution is. Another thing to consider, for ionospheric constellation design, none of this considers, scintillation, which is another question when you're looking at the ionosphere, how you would really, assess the impact of increasing number of data. And final point, I think, hopefully this maybe help motivate something like a Romex-like campaign where we had real ionosphere data that we could look at these effects in a real way, because, there's obviously some limitations to doing these Aussie experiments. And without real data, we can't say that, what you would really get. So I will stop there and take any questions. Thank you.
Thank you. I think we have time for maybe one quick question if someone has a quick question.
Thanks. That's perfect. Timely. You were talking about Romex-like campaign. That's something that we would like to do. But what I'm wondering, with this, your setup with MacMX and Dart, I'm assuming you can do an Aussie-like experiment and can kind of inform how do we want to distribute that 30,000 occultation over local time? Because as you said, the local time has a strong impact on the ionospheric specification, because Romex, if we do a Romex-like experiment, we're going to get data what really we cannot do in architecture design. So I'm wondering if you have given a thought of doing an Aussie-like experiment and really looking at how do we want to distribute those 30,000 occultations per day or uniformly over a local time period.
So you certainly can do that. I guess it comes back a little bit of, in that case, you have a large space that you can look through, and running a whole atmosphere model, there's a limited amount of experiments you can probably run, because it's a kind of expensive simulation to run. So that could limit, how much you could look. The only reason, you might want to do something like Romex is there's a lot of data potentially already there. So it maybe depends what question you want to ask, right? You can say, well, we already have potentially a lot of available observation, so why don't we look at that even if it's not perfect, versus are you trying to design an optimal new constellation? I think with this type of setup, you could do both.
All right, thank you. Thank you very much. I think we have to leave it there and move on to our next speaker, is Sergey